Hello and welcome. This is Chapter 6, Section 2, Part B. Here are our main objectives for today. So we're going to be talking about determinants today. First thing is to find a determinant, and we'll show you what that is in a moment. The first thing is that the matrices must have or must be a square matrix. So we must have a square matrix in order to have a determinant, which means if the dimensions are n by n. So whatever n is, as long as it's a natural number like 1, 2, 3, 4, 5, 6, 7, or 8, 9, whatever, as far as you can go. So the first thing is we're going to find the determinant of a 2 by 2 because there's different kind of ways of finding determinants. They're very similar, but a little bit different. So 2 by 2s are the first thing we're going to focus on. So a 2 by 2, which is in fact square. If we have a matrix A, and I'm going to put random coefficients in there like A, B, C, and D, we can find the determinant of A. So the determinant of matrix A is like that, or we can also write it as the absolute value symbol. This actually means determinant of A in a matrix context versus the absolute value. So some people get confused with that, but all that means is that means determinant of A, the matrix A. And the way you do that is you're kind of cross multiplying per se. So it's like A times D, but then we're going to subtract this C times B. So you're going to multiply A times D and multiply B times C or C times B. It doesn't matter. You could put BC first if you want, but then we would subtract the two. So we'd go along this one first, and then we subtract whatever that product is. And that is that determinant. Why are they useful? Well, they're very useful for solving system of equations. We're going to get into something called Cramer's rule later to solve them. It also allows us to figure out if a matrix is invertible or has an inverse. They can be used for area and volume calculations. They get into physics stuff with what's called eigenvalues and eigenvectors, which we're not going to get into, but it is very useful in more real life contexts. So let's just find the determinant of this. So again, to find the determinant of this, your determinant, it's not labeled as anything, so we're just going to do DET, and we're going to multiply this, which is 4 times 6, and then again, we will be subtracting whatever those are multiplied, which is -1 times a -1. And then we simply will simplify it. So that's 24 minus 1, or we get a 23 for that determinant. So that determinant, we'll get into a bigger one as well, and we're going to be using them very shortly. But let's first talk about something called the identity matrix. The identity matrix of some order n, again, it will be a square matrix, so that's why I have it, it's an n by n. It has to have a square. Notice that the diagonal, the leading diagonal, or whatever you want to call this, right here, starting from the top left and moving down to the right, these will all be 1s, and everything else will be 0s. That would be the identity matrix, and you can do it as big or as small as you want. Again, you could have a 2 by 2. If I just do a 2 by 2, that identity matrix will be this. If I wanted a 3 by 3, the identity for 3 by 3s is 1, 0, 0, 0, 1, 0, 0, 0, 1. Again, you have this diagonal of 1s, everything else 0s. Diagonal of 1s, everything else 0s. And you can continue this forever and ever, as long as you have a nice number, n, a natural number. So that is what a identity matrix is. And that's just like if you have the identity of multiplying. So just think about identity of multiplying is just timesing by 1. So if I say 4 times 1, that's still 4. So the idea is if we multiply by this to any matrix of the same size, it will give me the same thing. Same with adding 0. If I add 0 to anything, nothing changes. It will stay the same. That's why it's called the identity. So let's do a quick example of finding the inverse of a matrix. So the first thing is, does it exist or not? So the first thing I would like to do before I do a lot of work is, does it actually exist? So we just have to find the determinant of A. And if it is a non-zero value, it exists. So we're going to multiply across that. So 3 times -1, and then minus 1 times a -4, which gives me a -3 and a +4, which is in fact equal to +1. So therefore it does exist. So we know it exists, so now I can find it. So once you know it exists, that is when we're gonna go ahead and what's called doubly augment. So we're gonna rewrite it as 3, 1, -4, -1. And then we're gonna write the identity matrix on the other side of it. So it's a 2 by 2. First off, it has to be a square. Then what we do is we augment it, put that line, and then we put the identity of the same size. Now what we're going to do is we're going to do row operations to make this side the identity, and whatever is over here will be my inverse. So this is kind of how it is. Like this is A with an I, that's that identity. That's doubly augmenting it. We call it doubly because there's two rows here. And we use what's called Gauss-Jordan elimination to turn A into I now. So we're changing that to the identity. So let's work through that. So the first thing is, again, I like to have the 1 up in the top left corner, so I can actually rearrange these. So my thing, like we've been doing before, make this a 1, make this a 0, make this a 1, make this a 0, you're done. So if this is already 1, we just swap. So like I'm going to swap row 1 and row 2, which is okay to do. So I don't know how Alex does that, but I would do this on paper. So Alex might give you some funny things, so you might have to work around that. So if I swap them, I have 1, -1, we have 0, 1, and then 3, -4, and then 1, 0. I just swap them. Okay, now what I'm going to do is I'm going to use this 1 to get rid of this 3. Again, make this a 0, a 1, a 0, and then you're done. So how do you do that? So in this next one, well, we're going to take row 2 and we're going to subtract 3 of row 1's. And that is my new row 2. So again, if I subtract 3 minus 1 3 times, so I'm taking this row, minusing 3 times this to get my new row here. So let's move that up. So again, the first matrix is not changing. The first row of the matrix does not change. So 1, -1, 0, 1. Now we're doing 3 minus that, which gives me a 0. And then if I take -4 minus this 3 times, which gives me a minus a -3, which is adding, gives me a -1. And then we got like this one here, 1 minus 3 times 0 is still 1. And then 0 minus 3 times 1, which is -3. So now what I want to do is I want to make this a 1. So we can divide by -1 or times by -1 to get rid of that. So now I'm going to take row 2 and I'm multiplying that by -1 to be my new row 2. So let me move that up. So again, we're not changing at all that first row. That's still that. So we have 0, +1, now -1, and +3. Now, what's really nice is that this row won't change anymore because it's already perfectly done. But all we have to do is make this a 0, and then we're done. So if you notice, 1 plus -1 is in fact 0, which turned out to be nice. So we're going to say, well, let's take row 1 plus row 2, and that is my new row 1. And that will allow us to find our inverse matrix here. So as our final answer here, essentially, if we add it, we still have a 1 there. That's not changing. This is still 1, 0, -1, 3. Those aren't changing. We're just adding these 3 parts to these 3 parts, because 0 plus 1 is nothing, or still the same, sorry. So this ends up being 0 because we add those. We add these together, which is -1, and we add the other one together, which is 4. So 3 plus 1 is 4. So now we have our inverse. So this, let's highlight this. Right here is A inverse. So we made the identity here. So now we have the identity. Let's get my pencil out here. Undo that. Pencil, there we go. So we have the identity now augmented with our new, which is called A inverse. So this part right here is A inverse. So we're going to write it as A inverse equals -1, -1, 4, and 3. And that would be my answer for this. So let's do example 3 here, another 2 by 2 matrix. Let's first check if it exists before we try or do any of that work. So again, we first do this by finding what is that determinant of A, which if you remember, you can write it as the absolute value of A, which is technically called the determinant of A, but you remember these as absolute value symbols. Totally different. So when we do that, we kind of do this cross multiply kind of thing. So 2 times 4, and then minus that 8 times 1, which if you notice is 8 minus 8, or in fact 0. So that means it doesn't exist, does not exist. And if you remember, the word we're going to use is this is singular. So I believe if you do your homework, you should make sure you click this is singular. So A is in fact singular. So please try this one on your own. Check if it exists first, and then try it to see what you get. I will show you an answer shortly. So you should get that this is your inverse, -3, 5, -2, and 3. Just remember when you do it, make sure you augment it with the identity 1, 0, 0, 1. So again, you should make sure you have 3, 2, -5, -3, 1, 0, 0, 1, and then do a row operation so that this side then turns into that. When you do this, it's harder to get a 1 in the corner. I divided by 3 to everything here and made fractions, which is fine. You don't have to. There's a number of ways you could do it, but do your best, and hopefully you got this answer, and if you have questions, let me know.